Welcome. So this is a new module, so let's have an overview of what we have been doing. So we precipitation and measuring precipitation, evapotranspiration type and estimating evapotranspiration, measuring stream flow, hydrograph analysis, open channel flow. This would be generally in the surface hydrology class. In the soil science or also surface hydrology uh, class, you will also study like soil moisture, infiltration, and percolation. And in the groundwater hydrology class, we studied so far aquifer, we studied groundwater flow, and typically what would be the next step would be well hydraulics because that's an important topic in groundwater hydrology. Okay, so let's just get started with this new module. So the first, so these are from your textbook, Applied Hydrogeology. You can check like chapter 5, that is about well hydraulics. Or from groundwater project, you have a whole book about this topic. So that's like an introduction to hydraulic testing and in hydrogeology, basic of pumping, slug, and pecker methods. Yeah. So that's basically if you want to read more about the topics that we will cover in this module. Okay, and let's get started. Our first lesson would be like response of aquifer to pumping. So you have an aquifer and you install like a well, a pumping well or injection well or whatever it is, and then the aquifer will respond to pumping. We will learn here in this module, like first of all, we will learn how the aquifer will respond to pumping. Uh, and that would be the first part. The second part of this module will be to understand how to do aquifer tests. So aquifer tests, these are some of the investigation methods, like field investigation methods that we use to learn about the aquifer. Because remember, the aquifers, this is in the subsurface. How are you going to learn about the subsurface? So you can do like intrusive method like an aquifer test, or you can do like a non-intrusive method, which we will be learning in the next module, like geophysical imaging. Yeah. Let's just get started. Yeah. So this lesson basically it's just like a short introduction. So by the end of this lesson or this video, you should be able to describe the basics of hydraulic. Yeah. Like once we start pumping water out or injecting water in, and once we start pumping water out or injecting water in, how will the aquifer respond? So here, this is aquifer response to pumping. That would be like your participation question for like these three lessons, like because these are a set of three lessons. Aquifer respond to pumping, steady state, and transient drawdown. So that's basically you don't have for each video. You don't have to make this for each video, but you can just do one for just ask one question and answer any two questions. Yeah. Okay. So well. Yeah. Okay. Let's get started. So you see here, this is different uh, type of wells. So see, they look very different, and they also look very similar. Yeah. So like you see here, this is a borehole well. So this is a borehole well in a farm, and this farm is I don't know where, probably somewhere maybe in either North America or South America. I don't remember where I got this image from. But you see, it looks very similar to a borehole well in a farm in Egypt. So that's in Egypt. You can see the desert, and in the middle of the desert, you see this green area. How is it possible to have this green area in the middle of the desert? Well, thanks to groundwater. But now you see the similarity. Both of them are borehole wells. You have a borehole, and then you have a well. Uh, now here you see this is not like a borehole, like where you have a borehole and you put like this pipe in a borehole and you have a pump on the top that pumps the water. Here, this is called like an open pit well. And again, you see, uh, so that would be different than a borehole well, but you see the similarity. So this would be like some old open pit well, like in Germany. You see this old like architecture style, and similarly, you will see something similar to like in the Moroccan desert, yeah, an old well in the Moroccan desert. That's called an open pit well. Open pit well because you just put a bucket. So like in this well, you put a bucket, you drag the bucket in, you get the water out. That's how you can. Here you see this is like that's exactly what I was describing you. So here this is an open pit well in India, and you see each one is like um, putting his bucket in to get the water out. Yeah, and this is another well. This is a very kind of like a very technical well. This is not a pumping well. This is an injection well for CO2. Uh, uh, because remember one of the mitigation measure for climate change is that you get like power plants, they produce a lot of CO2. So the power plants, they have a stack, and like on this stack you collect the CO2 that's coming out from this stack. You turn it into something called like a supercritical CO2. Like you put it under high pressure and high temperature, you turn it something is supercritical. Supercritical, this something means that is something between it's like a liquid and a gas form, something in between. That's what's like a supercritical. And then you inject it in deep geological formation, and instead of like sending it to the atmosphere, you inject it in a deep geological formation. And in order to do this, that's what you'll have this very sophisticated uh, well like looking type of well. And again, so like you might think that wells are only like what like okay, pause this video. Okay, let's this is a puzzle for you, yeah. So I want you to do puzzles, yeah. Pause this video and think what are the most different usages. What are the different usages of well? I already like the most obvious usages is like water wells, yeah. And these are used like this is a water well, 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 this is a water well. That's the most obvious use. And so you extract the groundwater for like domestic, municipal, industrial, or irrigation needs. So here, for example, you see this is for agriculture need. Here you see this for like domestic like needs, for example, and so on. And here also, yeah. And I showed you like another example for the use of well, which is for, in that case, for injecting like CO2. Yeah. So I want you to think what could be other usage of well. Like why do like so people drill like so people we drill this well here to inject CO2. We drill this well here to get some water. Pause the video. Think about what could be other usages of well. Yeah. Just think about it. Yeah. And list at least try to list at least five. Yeah, that's critical thinking exercise. Yeah, just think. It's like a puzzle. I'm giving you a puzzle. Like, why would you drill a well? Yeah, I give you two reasons. Manusip, like water, extracting water, fresh water, and injecting CO2. What could be other reason or usages? Okay, well, welcome back. So let me tell you some other usages other than extracting groundwater for agriculture or domestic use. Other usage, this is, for example, something I've done before, which is to use well to control saltwater intrusion. Yeah. So there are different ways for doing this. One way is that they are called like scavenger wells, and in this scavenger wells, like what you do, you just like extract uh, for this scavenger wells, like that's what they call them. Uh, for this scavenger wells, what you do is that you extract like saltwater intrusion. What are other other thing is that you could like you can put like well like injection and pumping well to create a hydraulic barrier. So like instead of salt water intrusion coming instead of like the salt water intrusion coming uh, to where you are pumping. So basically, you put like a hydraulic barrier before where you are pumping, so that will like act like as a wall, and this wall will prevent saline water from intruding. That's one other use for that's like that's that's another thing. Uh, what would be another thing? Another application I already give it to you. Removal of contaminant from water. Like remember that remediation example at the beginning of the course where I told you you have like some type of contaminants that you cannot in situ treat because you cannot like vaporize them and they don't absorb. Like they don't vaporize and they don't absorb. So like the way to manage this contaminant situation is that you just put like pumping well to pump this contaminant out. What other thing for like a geotechnical and structural engineer? Why do they use well? Well, they use well to lower water table in a construction project. So if you are like a structure, geotechnical construction engineer, and you are at a construction project, you want to lower your water table to put your down your foundation or to do like the basement construction or whatever, then you just put like some pumping well around your construction site to pump the water out. What other application? Other application, remember we talked about like dam failure briefly. Yeah, we didn't talk about it like dam failure. And so one thing that when you, if you are worried about the structure integrity of your dam and like that it will not overturn like one remediation measure for this or one like one way to fix this is that you relieve pressure from under the dam through pumping the water out. Like if you have like excessive groundwater under the dam, you can relieve this pressure by pumping it. uh, you can also use it to drain like a farmland. Like if you're a farmland and you got flooded, or any flooding situation, like your farmland or other situation, and you got flooding, and then you can also put some pumping well. You can put a well to drain this farmland. Yeah. Uh, Another use is like not pumping well, is like injection well. So injection wells, these are commonly used. So dispose of like waste, like you get wastewater, you treat it, and then you dispose this in isolated aquifer, like deep aquifer, where you isolate this. Uh, or if you want to inject any fluid into the ground, like here, for example, when we are injecting this CO2, yeah, so that's like it's not a fluid, it's supercritical, something similar to fluid, or is this fluid like for different purposes, like for fracking, for example, like where you inject like fluids to frack to break the rock so you can get this non-traditional oil and gas resources. Yeah, so that would be another use of a well. uh, Heat pumps like geothermal energy. So in on like Long Island in New York, for example, groundwater is pumped for cooling purpose and then returned to the same aquifer by injection well. So you have this like cycles, yeah. Uh, so that is, yeah, that is another also application would be artificial recharge. That's like used a lot in California right now, where they do like this artificial recharge for the aquifer, and this is one of the management strategies. So you can manage the aquifer at different years and like during drought periods. So that's like also one mean for while you have well. Like, so you see, like it's a lot of application, yeah. You think it's only used for water, like for groundwater purpose, like agriculture or domestic use, but or industrial use, it has like a lot of application. You see here, I just put some art photo like this, like fine art, yeah, where like architecture at um, these architectural marvels. So these are ancient and historic wells that you wouldn't see much of them now in use. But for example, this is like a holy well in Santa Cristina in Italy. It was about, yeah, it's just like about 3,000 years old, more than 3,000 years old, about 3,000-year old. And here is another one, like something looks similar in Peru. It's about like also like 2,000 years old. And these spiral wells here, like see, this is another spiral well. So if you go inside of these, and then you have like spiral wells with this staircase that go all the way to the groundwater, to not to the ground, yeah, to your water table. So you keep taking this stairs until like you reach your groundwater. And we don't know if these wells were constructed to fetch water only, or they also have some spiritual purposes or religious purposes other than just fetching water. Like that's like not very clear, but you see it across different culture, like in South America, in the American North and South America. You see it in uh, India. You see it in Europe. Here is another one, like in Europe, and like you see, the water table is here. This is probably like one of the, yeah, like this well is in the oldest city in the U.S. St. Augustine in Florida. So you see here, that's St. Augustine in Florida, and that's probably, yeah, this is, you see here an old well there. Okay. Uh, well, have been associated with women and children also across culture. So this is like here in Asia and Japan and Africa. Like you see women, you see like happy children. It's a very happy situation. I've done this when I was a kid before. Yeah, when I used to my yeah when I used to go to farmlands, and I would like see this guy. I didn't do like this guy because they mainly were motorized. Like they had a pump, like you have this pump and with a motor, like an electric motor and or not electric or gasoline motor, and then like but you see the water was like gushing out, like similar to what I showed you here. So. Uh, See something like this, and then you have this pool where you find this very nice water coming out of it. Yeah, it's very like uh, you see, like you'll be naturally happy like this. But you see it across culture, like in Europe and across like native communities. So you see this across culture. So a lot of work, yeah, a lot of workforce is spent in fetching water, yeah, from and that's mainly by women and children, yeah, and so a lot of work, like manpower or like women power and children power, is for fetching water. Well, like you go and fetch water, and you see like women would be like will go. Sometimes they can travel for long distance. I once reviewed like a paper about it, like sexual violence among women, how it is related to water table. Can you believe this? That you can relate like water table level to sexual violence among women? And this study was basically saying like during drought period when water table is low, the rate of women rape could like increase. And that's the reason for that is that because women will travel for like longer distance or much longer distance to get water because the wells near where they are or in their area could be dry, so they have to travel longer distance, and that could increase like sexual violence against women, for example. Yeah. So I once like reviewed the study it like this. Okay. Okay, so let's move forward. Wells are also related to contamination, and we talked like in the introductory video. Remember, we discussed some of like Erin Brockovich movie and Blackwater movie, where you have this contamination scenarios. You have like dump site, for example, by an industrial facility or a pond that does not have lining, and then the wells in the nearby communities, they will use this water, and then they will you will find some systematic illnesses appearing, like whether carcinogenic or non-carcinogenic. So that is like an example of one of the first contamination stories that was very well documented in the early 19th century, when cholera started to outbreak in London. And the reason for this, that was by John Shaw, like Snow. He was, if I remember correctly, I think he was engineer uh, in I don't remember if he was an engineer or a medical doctor. Most probably like a medical doctor. I don't remember, but you can read the Wikipedia article, check whether he was. You can write for me in your exit ticket, like check it in the Wikipedia and say whether Jon Snow was like a medical doctor or an engineer. But like when the cholera outbreaks, that's what he did. He started to produce a map of where these cases were documented. So he started to like draw like, oh, I got a lot of cases here, I got some cases here, I got a lot of cases here, I'm getting a lot of cases here. And then he started to plot also on the same map. So this is like Broad Street well. In the same map, he started to plot the wells that are the nearby well, because what he suspected that this is some water prone disease. Because what happened at this time is that people they used to get water out like using these wells, but they didn't have wastewater treatment or wastewater uh, network. So basically, like the waste will be that the wastewater will just go contaminate the water that they are drinking from, and that contamination led to the outbreak of cholera. And what he did, he figured out that it is this well where this is where people are getting this water from, and that's why, like, see, this is all these cases are around this well. And what he did, he went there and he removed the handle of this well. Yeah, so you see, like, this is a well. See, this similar, like, see this handle that this guy is using to get the water out. He removes this, pumps the water out. He removes this handle, and this is a replica. Like, if you ever visited London, the Broad if you visited like the Broad Street in London, you will find that they put a replica for a replica pump with the handle taken off the handles that Jon Snow did, like so that people will not use this water source. Yeah. Okay. Uh, uh, Now, in this lesson or in this module, we will not gonna learn about like how to drill a well. That's not gonna be part of it. I did this before, by the way. I did this before when I was working, doing like some field work, and for this field work, we needed to drink like two wells. And, that was an island. We needed to drink two wells in monitoring wells to monitor like nitrate in the groundwater. And we got like, you see this, you get this, get a driller like a big auger like this one, like, so this is driller or a big auger or driller. So you get like one of these, and you start like, I think we had like, we need to go like, it was a car similar to here, and we need to go like 50-meter down. I don't remember. Yeah, I think it was about 50-meter down. Yeah, we want to go about like 50-meter down, like drills as well. And it's not cheap. Like, I think each one will, I don't remember how much, maybe 20,000 euro. Yeah, for each one, like to just drill like this well, to get like this auger and drill this well. And it's time consuming. Like, it took us, I think, like 3 days. Yeah. And for this, before we drill this well, we need to find where would be the best location to drill it. Yeah. And for this, we did some geophysics, electrical, electrical resistivity tomography. We will learn how to do this, and we will do like a field trip also, like a field trip. Like, there is a field trip, like for field trip information would be on Canvas, like for how to do this imaging. Yeah. But anyway, so I'm not gonna cover like this detail, like how to drill a well or how to develop a well after you drill it. But there are excellent like hydrogeology field manual where you find these details, like drilling well and well completion. Like after you drill well, how you do the well completion. I have a couple of these the books or field manual in my office. If you are interested in looking at any of these books, please stop by my office and you can have a look at them. Yeah. Uh, okay. So let's get to our lesson. So this is our lesson is the response of aquifer to pumping. So guess when you start pumping, guess what will happen? Yeah. Obviously, your if you are in a unconfined aquifer, your water table will drop because you are draining this pore space. Yeah, so you are draining the pore space. So let's say this is your initial water table. Yeah, and then here you have like a pumping well here, and then once you start pumping, what will happen? The water level will drop. You will have like the highest drawdown. So like from here to here, that's called the drawdown. The highest drawdown will be closer to the well, and it gets smaller and smaller as you go away from where you are pumping. So you're pumping water out, and then that's like your water table, and then your water table will drop. Yeah. So that's like after pumping. Okay. Uh, but the water and if you are like pumping from a confined aquifer, the water level will not change. Like if this you're pumping this from a confined aquifer, so if you are pumping this from a confined aquifer, so let's say here this is like you have a confining layer here and you have a confining layer here, and let's say this is your potentiometric surface. Yeah. So what will happen? The water level will not change, but your potentiometric surface will change. Yeah. So your pressure will decrease here. Yeah, because you are releasing water from pressure. So the water pressure will decrease here. Okay. But what will this depend on? Like the aquifer response to pumping will depend on what? It will depend, of course, on how much water you are pumping out. Like, so if you are pumping so a lot of water, you will have more drawdowns than if you are pumping less water. It will also depend on the number of wells. If you are pumping, if you have more pumping wells, then the potentiometric surface will, and you're pumping from all of them, then you will have more drawdown, yeah, or less drawdown, or your drawdown will change, yeah. It will also depend on the well condition, like whether it's like partially penetrating or whether it's fully penetrating. And we will look at these details later. Like when you have like a partially penetrating, let's say, let me show you what's so that's like your unconfined aquifer. Fully penetrating means that like your screen is here. That's like your well screen is here and here, and you are just like pumping from through like you're screening all the aquifers. That's like a fully penetrating. Partially penetrating would be something like this, yeah, like your well is here, but maybe your well screen is only here. Yeah, so that's where you are pumping water out, like just from this part. So that's like partially penetrating. That's like where you are pumping water from. Yeah, it could be also, yeah, could be also like this, yeah, partially penetrating. Uh, It would be also like a steady state or unsteady state. Like would you reach it like a state of equilibrium where you are no longer having a drawdown or you are still. So let's say like let me give you an example. Yeah. So and this also related to groundwater sustainability. Important aspect related to groundwater sustainability. So let's say like I have a river here maybe, and then I'm pumping from here. So what will happen, like once I start pumping, I will like have like a drawdown like this, maybe. Yeah, I'll have a drawdown like this, and maybe then like draw down like this, and then like this, and then like this, until I start like tapping, like getting water from here, not from storage anymore, but from this river, and then like this will reach a steady state. Like I will, like you will see, like you're pumping water out, and you will see that your water level is like a steady state, is not like decreasing, and then you say, "Oh, nice." This is called like this is called groundwater capture. Like your water level are not decreasing, so you think you are using this sustainably, while actually what is happening is that you are getting this water not from groundwater, you're getting it from surface water. So you are capturing this from other sources. That could be surface water, that could be spring discharge, that could be spring here is discharging, so you'll find the spring discharge is becoming less, or submarine groundwater discharge is becoming less, or like the water level uh, at your river is like falling down. This is called groundwater capture. But anyway, so that would be an example where you reach like steady state, where you are no longer like your water level is no like your drawdown is constant, it's no longer changing. That's called like steady state. Okay. Uh, Aquifer type, yeah. Whether this is like confined, leaky, confined, or unconfined, so that will also control like your aquifer response to pumping. So in a confined aquifer, your water table will go down. In unconfined aquifer, your water table will go down. In a confined aquifer, your piezometric surface will go down. In a leaky confined aquifer, you could increase leaking because you are uh, lowering your drawdown, and that could like you could increase the leaking, or change it, increase it or decrease it, depend on like the subsurface. Yeah. Of course, it could be also homogeneous and heterogeneous, and isotropic versus anisotropic. This all will affect like your pumping and the efficiency of your pumping well. Yeah, and how you design your pumping well, as we will talk about this later. Yeah, by towards the end of this module. And the size of the aquifer, like large with nearby boundaries such as no flow or a stream. So if you have, think about it, like you have like your nearby boundary is a no flow boundary. So if there is no flow boundary, you'll find drawdown will be very fast. If it's the stream, drawdown will be very slow, or you'll not even get any drawdown because water will be replenished from the stream, versus here water will not be replenished because like you just pump the water, your water level will go down. Yeah, if you are in a confined aquifer, your water table will go down. So uh, and then, of course, the aquifer parameters like hydraulic conductivity, transmissivity, and the storage coefficient. This will all impact your aquifer response to pumping and your drawdown. And I will show you like equations for this. I will show you like when you increase hydraulic conductivity, are you going to get more or less drawdown, and storage coefficient, and so on, and transmissivity, and so on and so forth. So let's look at some examples. Yeah. So here, aquifer response to pumping. Like, what is the objective here? The objective here is to estimate drawdown, like decline in head, in hydraulic head, at various location and time. Yeah. Uh, so here, uh, like what you see here, uh, you have like two pumping well, like you have one pumping well here and you have another pumping well here. So you have like this pumping well, this was like your original water table, and then after you pump, like you see here, this is where you get like the maximum drawdown, and here for this well, this is where you get the maximum drawdown. Here, like you see, these two are interacting, so like this is the cone of depression of this one. Yeah, and this is the cone of depression of, oops, of this one. And see, when the cone of depression of this one interact with the cone of depression of this one, then they created like this drawdown here. So here And we will learn about all these cases. So here you have a drawdown here, you have a drawdown here. Here sees a drawdown like as far like the more you go away from your pumping well, the drawdown will be here almost like zero. So the drawdown here is zero, the drawdown here is maximum. Yeah, the drawdown here is maximum. And like the further you go away, the drawdown here will be zero. But like you see, the drawdown is not constant. Yeah, and that will depend on all these factors that we discuss. And we will look at this in details and in the equation. So here, for example, you see this like cone of depression, they take like this circular shape. And this circular shape is very important because we will like learn how to take advantage of these symmetry. Like you see here, there is a symmetry here. Uh, because like this cone of depression like has a symmetry, like you get like this circle, yeah, this circle, like see here, this is the steepest, and here this is like more gentle, like gradient. So here you have the steepest gradient, here you have like that's what you see here, like these, this is very steep, this is more gentle, and this is very gentle, yeah. Here, see the slope here is gentle, the slope here is steep, and here is the steepest. Okay, so you see this, but the most important thing you see is that this goes like in a circle, and which means that we can, instead of having like a Cartesian coordinate like x, y, z, we can have like a polar coordinate for our ground, like we can write our groundwater equation uh, in a polar or cylindrical coordinate, yeah? And then that will, like, we will see how this could help us to find analytical solution easily. But anyway, you see here, like the drawdown here is maximum, like here's negative 20, negative 16, here might be, I don't know, maybe negative 24 or whatever, yeah? That would be the maximum drawdown. So this is like when you, for example, reach a steady state. That like these heads are no longer changing with time. Like you reach this steady state. Like you get this drawdown as no longer changing in time. But also it could be like a transient case. Like drawdown could be a transient case. That's like an example. So let's say here's that's a good example. I like this example because it could show you like one of the consequences of pumping. Yeah. So here, let's say you are like you are small, you have a small house or farm here, and you have this well for like domestic use. And then some large farm or some industrial facility or some big user came and drilled like this deep pumping well. And here's the well casing. And then he will start pumping, and like you see, this is the static water. So this is before pumping. He will start pumping after 1 month. That is the drawdown that you get. Yeah. So you are okay. So that's like that's where your water is. Yeah. And then like after 2 months, that would be the drawdown. Okay. So you're still getting some water. Yeah. After like 4 months. Yeah. Now see here after 4 months, where is the drawdown? Now you're still tapping into some water, but after 5 months, that's the new groundwater table. And now you like see now this is the cone of depression. This is your new water table. This will become a dry well. I was once teaching this lesson and one of the students mentioned, oh, he said that's exactly what happened to my domestic well. It got dry because of nearby pumping, big pumping, and then it got dry because of this like one big user. Yeah, so like, and then you will find that like this well will become dry because now, so like this well here, that was the original water table before you start pumping from here, but then after 5 months see the water table became like below like your pumping well, so that would be like dry. Okay. So I think that's all for this lesson. This was just introduction. Next lesson we will learn about steady state drawdown.